Hey guys, so now that we've finished chapter 14, it's time to move on to chapter 15 because your next test is going to be on 14 and 15 together. And right now I'm planning for that test to be a week from today, okay? When you're watching these videos, a week from today. So what that means is if you have questions, you really need to be emailing me about you, not necessarily email me about them, right? You need to be discussing them in those discussion sections, right? Because if you email me, only me and you see it. But if you send it in the discussion section, then we can all see it, okay? So make sure you're using those discussion questions for your answers or for your questions and answers about homework and lecture, all right? So we're going to move on and talk about chapter 15. So first of all, why? Chapter 15 is all about equilibrium. We've kind of talked about that already, but equilibrium is necessary to human life. Okay, and what we mean by equilibrium is you see this nice little sort of double arrow here. And what this means is this reaction can proceed in either direction. We talked about this a little bit last chapter. We started introducing it. But the hemoglobin and oxygen can combine to form this new compound that contains them both, or that new compound can decompose back into the single hemoglobin protein and the oxygen. And why this is necessary is this dynamic equilibrium allows us to maintain the oxygen level in our blood and to carry it different places. Sometimes some places may need more oxygen, some places may need less oxygen, hence why it's important that this is reversible, right? So think of like your lungs. Your lungs, you want to have a high concentration of oxygen. So the reaction favors the forward progression towards the production of this component that has the hemoglobin and the oxygen bound together. Whereas in the muscles, you don't need a lot of oxygen. So the reaction actually tends to proceed more to the left, and you end up having more of just the pure hemoglobin and the unbound oxygen because we have a low oxygen concentration in our muscles. Okay, so that's really what we're going to be talking about this chapter is the importance of these equilibriums, and we'll talk about how you can predict if an equilibrium favors the products or if it favors the reactants, and how manipulating a reaction may cause it to shift to the right, which means to the products, or to the left, which means towards the reactants. Okay, so when a reaction starts, right? So let's start with the basic just example. We have reactants that are being consumed so that products can be made, right? And as the reactant concentration goes down, the product concentration is going up, right? That's exactly what we're saying. And we also talked about how this affects the rate as well, right? As reactant concentration goes down, so does the rate, right? So as this is proceeding, you're ending up with less reactants, more products, and the rate is slowly diminishing. Well, what happens is eventually you end up with so many products that the products can actually react with each other to reverse it and start making more reactants. Okay? Assuming that you have a closed system, right? The whole idea of an equilibrium is assuming that it's a closed system. So, like our body, our blood is in a closed system. You know, when you develop a dynamic equilibrium with boiling water in a pot, you have a closed system because you have a lid on it, okay? So, we're talking about a closed system here, but basically, the product concentration is increasing, and eventually it's going to start reacting together to make more reactants. So really what that means is as the rate of the forward reaction is going down, the rate of the reverse reaction is actually going up, and the dynamic equilibrium is going to happen when those two rates meet each other. Okay, so the rate of the forward's going down, the rate of the reverse is going up, and then eventually they will hit. And when they hit, that's when we say that we are at a chemical equilibrium, okay? So whenever we're talking about a reaction that has the ability to go in both directions and generate an equilibrium, we say it's reversible, okay? And we use this arrow. Notice this is not a single direction arrow. These are two half arrows going in opposite directions, okay? And so I've already said this, right? But the forward reaction is slowing down, the reverse reaction is speeding up. Eventually, they hit the same rate. The definition of a dynamic equilibrium is when the opposing rates are equal. So since one's going down and one's going up, eventually they will hit each other. And whenever they hit each other, that's the chemical equilibrium. And at that point, however many reactants you have and however many products you have, those concentrations are no longer going to change. It doesn't mean the reaction stops happening, but it means that the conversion rates are now equivalent, so it doesn't look like anything is happening, even though there is still a reaction taking place. All right, so let's look at an example from a graph perspective, because I feel like this would really help, okay? So as the system approaches equilibrium, both the forward and the reverse reactions are occurring. So here is, so for the forward perspective, if I were to write a rate law for this, saying that this is a elementary reaction, so I can do that. Rate would be equal to K times the concentration of N2O4. And here, that's what they're saying. They're kind of representing this as KF or K forward, right? And as time is proceeding, the rate is slowing down. But if we consider the reverse reaction, then this would be your reactant. So rate equals K times the concentration of NO2 squared. So Kr, K reverse times the concentration of NO2 squared, and you notice that it is increasing over time. And eventually these two hit each other. And once those two hit each other and they are the same, they don't change after that point. Okay, equilibrium is achieved and the rates stay the same. Basically, it doesn't mean the rates can't change. What it means is the rates will only change. Hey, 1 second, let me stop the cats. All right, sorry about that. I swear they're playing. It doesn't sound like they're playing, but they actually are just playing, but they play really loud, so kicked them out of the room. All right, so once equilibrium's achieved, the rates don't change unless you do something to manipulate it. Now, you can manipulate the equilibrium, and then it's got to re-find a new one. And we'll talk about that at the end of this chapter. But assuming we don't make any changes, the equilibrium's not going to change. Okay? Now, let's look at this graph a little bit differently. So now we're plotting time versus concentration. So the concentration of the reactant is going down. The concentration of the product is going up. But what do you notice? Once we hit this equilibrium point, which we've already defined to be when the rates are equivalent, the concentration of the reactant doesn't change anymore. The concentration of the product doesn't change anymore. Okay? Now, they're not the same, right? You have much more concentration of product than you do reactant, but once we hit equilibrium, each one is a consistent value. Okay? So be very careful. Don't assume that equilibrium means everything is equal. What's equal in an equilibrium are the rates. The concentrations between the reactants and products don't have to be equal. In fact, it is incredibly rare for them to be equal. Usually, a reactant is what we call, or an equilibrium is what we call product favored, meaning almost all of the reactant has been consumed to make product, or we have an equilibrium that's reactant favored, which is the exact opposite. Not very much reactant was consumed at all, and we hit our equilibrium. Okay? So let's define how we can express this in a mathematical representation. So before we include the numbers, we need an expression, okay? So we're going to start with the example we've already talked about. And we've already talked about how we can define rate laws for these. Okay? And what did we say? The definition of an equilibrium is when the rate of the forward equals the rate of the reverse. Okay? So rate of the forward equals rate of the reverse. And now what have I done here? I've said, okay, here's that exact statement, but now let me substitute in for these rates their rate law expressions. Okay? I can then rearrange that, just a little bit of algebra. So I divided both sides by K reverse, and I divided both sides by N2O4 to get my K's on one side and my concentrations on the other. And we get this expression. And we call this expression, this is a law, okay? It's a law, and it's called the law of mass action. It was developed by this guy with this epic name, Cato Maximilian Goldberg, and then Peter Wage. and they developed this expression. But at this point in time, we have said, let's simplify this. Instead of this being little k over little k, let's just call it a big K and be done with it. Okay? So this big K, what do you notice, is equal to the concentration of, what's this? NO2 is a product, divided by the concentration of N2O4, which is a reactant. And this expression will not change unless you change the temperature. Why? Because what did we talk about last chapter? Little k is temperature dependent. So if big K came from little k and little k was temperature dependent, then big K also has to be temperature dependent. Okay? So let's go to our generalized reaction. You guys know I like bringing this guy up whenever we need to introduce a new sort of expression. Okay? So this capital K is going to be equal to the concentration of the products over the concentration of the reactants. So we have KC. What do you think the C might stand for? What did we talk about in the last chapter? What does brackets mean? Brackets means concentration. So it's just saying what the capital K is. All right? So concentration of the product, C, raised to its coefficient, times concentration of the product, D, raised to its coefficient, divided by concentration of reactant A, raised to its coefficient, also divided by the concentration of reactant B, raised to its coefficient. Okay? This is called the equilibrium constant expression, and this is a unitless value. Now, I'm telling you this because if you put units in this, they may not necessarily cancel, but K is meant to be an expression of, in the most general sense, product over reactant. And if your products and reactants are in the same units, then they should cancel. Now, depending upon what these exponentials are, it may not look like they do, but I am telling you, K is a unitless value. Kc, which is the equilibrium constant, is a unitless value. Now, in this chapter, we're going to introduce another capital K, okay? And we're going to call this capital K P. And it is essentially the same thing. It just means that we're dealing with a reaction of gases, and we measure the concentration of gases with pressure, okay? But Kc, Kp, same expression. Guess what? Next chapter, we're going to introduce Ka and Kb and Kw. And guess what? They're all this general idea. All the subscript is doing is it's trying to define what the capital K is expressing, okay? Because it's an expression. So we're defining the expression. But the expression is the expression, and it is always products over reactants. So let's do a quick practice. All right. Now, I know these are gases, and I already mentioned Kp, but we haven't gotten there yet in the notes, so we're going to treat this as a Kc, okay? So Kc is equal to concentration of O2, you don't have to write the phase, cubed, products, divided by reactants, concentration of O3 squared. Okay, let's look at another one. All right, what about this one? Now you have two reactants in one product. Remember, it's always Kc equals, so Kc is going to be equal to the concentration of NaCl, brackets, squared, divided by the concentration of NO squared, also divided by the concentration of Cl2. Now, I note, common mistake here is people will try to add these. These two reactants are not added, they are multiplied. Okay? And the last example on this slide, in this case, it's still the exact same thing as the last one, okay? But what do you notice? You have some ions involved here. You need to put the charges of your ions in your expression, okay? Because silver, which is Ag, is different than the silver ion, okay? So ions, you do need to represent their charges in these bracket expressions, okay? So we've hit our time limit for this video. I will see you in the next one.